Hello, everybody. Can I have the next slide, please? Mars is a very attractive planet in our solar system, which looks red, far away, and mysterious. Those alone are reasons why we're interested in going there. But actually, what are the other reasons? Can I have the next slide, please? Here we can see a picture that was captured by the rover Spirit, NASA's rover, and it is a stunning view as the sun sunk below the rim of Gusev crater on Mars. So it is believed that Mars is the second planet that is hospitable in our solar system. It has plenty of minerals. Its average surface temperature is about minus 60 degrees Celsius. It has a thin atmosphere, and apparently there are traces of water. This is why there is a very competitive focus on the aerospace technology nowadays in order to land and build a potential habitat on Mars. Can I see the next slide, please? So astrobiology and the search of life. Here we can see two images. The first one on your left is a high-resolution color photo of the Mars surface, which was taken by Viking around 1979. It shows a thin coating of water ice on the rocks and soil. And the picture on your right is a Mars Express view of the South Pole, of Mars's South Pole. You can see the bright white region of this image, and it shows the icy cap that covers the Mars South Pole, and it's composed of frozen water and frozen carbon dioxide. Surprisingly, that the discovery of life on other planets and moons in our solar system is one of the most important challenges of our era. So looking for traces of extinct life on Mars enables the question about the origins of life, and this is a very fundamental question for humanity. So when scientists examine the Martian landscape, they notice characteristics such as rushing streams, river valleys, basins, and deltas that are undeniably the result of flowing water in the past. Can we see the next slide, please? Here we can see the mapping of the gravity field by the NASA Goddard Space Flight Center in Greenbelt. And as it was mentioned previously, planet Mars underwent a tremendous transition during its development. While life began and was booming on Earth, Mars's environment changed drastically, and we want to know why. Planetary geologists can look for clues in rocks, sediments, and soils to learn about the history of the planet's surface. Meteoroid impact craters, volcanoes, and other indications of atmospheric or photochemical effects and geophysical processes all bear witnesses of Mars's past. Next slide, please. And of course, space exploration has always been a catalyst for technology and innovation. Just think how many inventions were used for space projects before becoming commercial. Solar cells, insulin, freeze-dried foods, air purifiers, and many, many more. And now I hand over to, actually, I think I will continue, if that's okay. Can I see the next slide, please? All right, so a very useful discipline for the exploration of Mars is geomatics. And in this case, that could involve also geospatial technologies. Actually, geomatics is the science that integrates gathering, storing, processing, modeling, and analyzing spatial information. As you see here, it incorporates many different disciplines, such as GIS, geographic information systems, global positioning system, hydrography, mapping, photogrammetry, and many more. I'll say a couple words for GIS. The geographic information system manages and analyzes and maps all types of data. This is very useful because it could involve a combination of satellite images mosaic that could be used potentially for navigation and can create 3D images that can show the landing place for the Mars rovers, and also can model a present data set with the largest craters, canyons, and other characteristic objects. GNSS can assist with techniques in geodesy that can revolutionize the geodetic measurements and assist with this task. Photogrammetry can help to reconstruct, for example, craters using multi-scale imagery. Next slide, please. Yes, as you can see here, geomatics can be used for the industry on Earth, explorers and settlers, and also private industries as mining. And the innovations, as we mentioned before, 3D mapping. We also can implement big data tools, autonomous and intelligent systems that we will discuss in a bit. And next slide, please. So yes, geomatics can be achieved, incorporated many different technologies, such as artificial intelligence and robotics. The already mentioned 3D geospatial visualization, autonomous technologies that are used right now in rovers. We will provide with some examples later on. Local intelligence and sensor-based logistics, machine learning, which is also already implemented, and UAVs. Next slide, please. And now I hand over to my colleague. Thank you.
Thank you so much, Evangelia. So I'll be talking about the surface mapping. We all know that there are satellites hovering over the Martian surface, which can do remote topography mapping with UAVs and rover. And with the latest technology, we are having UAVs, but in future, we are talking about swarm of UAVs. So under the topography mapping, we have intelligent automation, as in the rovers as well as the UAVs and the satellites will be trained, and the machine learning will be applied such that they can take their own decisions and select the locations wherein they have to map, they have to study, do the thermal analysis, thermal spectral analysis. And in such cases, AI is the ideal for a hostile environment, so that it doesn't risk human life. You don't have to go there. It can take their decisions autonomously and give the desired results which we want. Also, we can't neglect the importance of remote sensors and satellites. Sensors are also of utmost importance because not everything could be captured through imagery and thermal analysis, but also remote sensors give us an idea what lies beneath the surface of Mars. So talking about the mixed reality 3D geospatial visualization, with the data that we have gathered via satellites and UAVs, we can construct the real-time interactive simulation environments. And we can use this kind of simulations to map the surfaces, to find out the locations where we can land the rovers, land the future human missions. Out of this, we can also reconstruct the 3D scenario scenes, and the base maps and building data are contributed by Bing Map and OpenStreetMap. So it's an example which is currently been in the market. About so right now we saw about the surface mapping, which was the remote surface mapping, but now we'll be getting onto the surface via robotics for exploration. So we are not new to the swarm robotics concept, as it is still evolving on Earth, but we soon think that it will be a key Key contribution of swarm robotics, like rovers and UAVs and robots working all together on the Martian surface without being controlled by humans or ground station here on Earth. They will be able to communicate with each other, take the decisions, find out their own mistakes, and improve from their own mistakes. And apart from just surveying and mapping the surface, they'll also be performing activities like drilling, mining, and testing different samples, going into the regions even the satellites could not capture, go underneath the surface to figure out what's the geology of Mars. Apart from just drilling mining activities, there are certain studies like seismic activities, magnetic fields, and regolith variations, which also need certain kinds of sensors. So these robots will be having active feedback control system. Depending on what readings they get, they will change their parameters to take the best possible readings. Um, okay, I would like to hand over navigation part to my colleague.
Next slide, please. Thank you. So actually, navigation is pretty tricky on Mars. The rovers cannot be controlled on real time. It takes around I'm sorry, the slide we see, it should be the previous slide. Yes, yes, here. Yeah, no. The previous slide, please. Previous. Okay, thank you. That's the slide. So as I was saying, navigation, the navigation of the rovers can be quite tricky. They're remote controlled and they are not operated in real time. It takes for communications from 3 to around 20 minutes. So these elements that you see in the presentation are used. So the antennas are a part of the DSN network, the Deep Space Network. They're located in California's desert. That antenna is Goldstone. Then another antenna is in Madrid, Spain, and another one is in Canberra. To steer the rover, we need to have maps. Mariner 9 made an extended mapping, but since then, our maps for Mars got only better. Depending where the rover is, the global map has a resolution anywhere from less than a meter up to 100 meters. So the NASA Jet Laboratory engineers use base maps and mathematical techniques to actually point the rover on its way to Mars and land it within a few kilometers of the target. Same happens with the descent imaging, pinpoint the rover within a meter or two on the surface. I can provide some examples for Curiosity and Perseverance. So Curiosity takes a series of stereo images around the rover with its navigational cameras. And this happens when it finishes for the day, because we actually want to operate the rovers during the day. The data gets sent at night, and then the rover makes a mosaic from the overlapping images and projects it into the ground. So the software that is used is called AutoNav, and there are two different sets of software that are working in Curiosity. It is similar like human walking. We look ahead to decide where we are going, but as we walk, it is necessary to change our route in order to avoid obstacles. Actually, the one who has two sets of autonomous navigation software is ExoMars, because this combination would add more flexibility. The idea is that one might turn out to perform better in a difficult terrain, while the other one might move faster when the ground is easier. Finally, for Perseverance, this called This so-called AutoNav software is more enhanced. It makes 3D maps of the terrain ahead, identifies the hazards, and plans a route around any obstacles without additional direction from controllers back on Earth. It is sped up about 4 or 5 times and is driving a lot faster than Curiosity demonstrated. Next slide, please. So the actual advantages of autonomous navigation would be to have a better positioning accuracy up to 100 meters in a circular peripheral, 24/7 relay to and from Earth, reduction of positioning errors, and especially reduction of surveying and risks of losing the mission. Next slide, please. I would like to hand over to my colleague, Rachel.
Mangai?
Yes, thank you, Rachel. Rachel, could you go to the geospatial technology sensor-based navigation slide, please? That's right, thank you. So one more form of geospatial technology is the sensor-based navigation. And one such example is a FedEx innovation called Sense Aware ID, which was recently launched just last year. And it uses this Sense Aware technology that's comprised of a compact sensor to track shipment cycles of the vaccine. And it's a lightweight sensor device that can connect to the Wi-Fi around the FedEx network by using its Bluetooth low energy technology. And this type of location intelligence provides vital insights that can help in preventing and mitigating risks before and during space activities on Mars. Next slide, please. So far, you've heard about all the different forms of navigation and surface mapping technologies that we have at our disposal. But what is the potential for the human settlement? While the Earth is 93 million miles away from the sun, the Mars is some 49 or 50 miles more further away from the sun. So the combination of this added distance and the elliptical orbit of Mars means that 1 year on Mars lasts 687 Earth days. And actually, Rachel, can you, next slide, please? And while orbiting the Earth, much like Mars has a tilt in its axis, a very similar value at 25.19 degrees axial tilt versus Earth's 23.44 axial tilt. And this tilt is what causes all of our seasons. So because of the slight deviation for Mars, we have longer seasons. And that is something that would definitely affect our livelihood for Martian settlers, as well as the weather patterns of Mars. Mars encounters dust storms and a different magnetic field, and their very thin atmosphere also poses challenges for example, flight, as we saw in recent news. But similar to the axial tilts, another commonality that we have is the polar caps. And these polar caps may reveal the planetary history of Mars. And both the northern and southern Martian ice caps, they change in size as the seasons change. And since we believe that the northern cap most likely has frozen water and the southern cap has carbon dioxide, we would most likely be utilizing resources from the northern polar cap. And the gravity also is 38% of Earth's gravity, so that will also affect how we mobilize on the Earth, on Mars, how much traction our rovers and equipment need to have to make sure that in case we hit any obstacles at high speed, that we have mitigation strategies in place. Yes, I believe this slide is for Evangelia. Babit.
You can move ahead. I'll speak to this later. Good evening. Thank you. Can you move to the next slide, please, Vishal? So a lot of the technologies have been discussed already in terms of future missions to Mars. The autonomous agents, which can be augmented with AI, as well as having data center level computer processing at the edge and open source sharing of geospatial data to create more AI apps that can be used both on board spacecrafts and on the surface of Mars. And Vishal also spoke about the use of swarm intelligence for UAVs, or aka drones, that can interact with each other. And this technology is actually being developed at the University of Toronto right now for use on the moon and the lava tubes on the moon, but which can also be applied in the future for Mars missions. And also we have AI being used, as Vishal mentioned, to explore craters, which can be used to explore craters on Mars. For example, the Mars Reconnaissance Orbiter has been using AI as well. So AI and machine learning in particular, which is a subset of AI, it's being used in all of the rovers that we've seen recently, and this is why they have been so successful as opposed to the previous Mars exploration missions. Because we have autonomous navigation, we can use intelligent targeting software, we can use remote scheduling and planning, and in particular, precision landing, which was used both for the Mars mission as well as the Chinese Zhurong, which use 3D laser scanning, LiDAR, and AI for their terrain data and elevation and obstacle avoiding mode. All of this was facilitated by optical cameras, which was used at 20 meters above the surface of Mars. Autonomous systems control, I'm going to talk about that a little bit later, as well as environmental monitoring for human safety. We can use AI for that. And we already discussed swarm intelligence, but we could also use machine learning and AI for modeling and forecasting dust storms on Earth to improve future prediction on Mars. Next slide, Vishal. So systems control, automation. This has been used on with computer vision-based detection systems. And there's also another technology, Spark, a deep learning-based terrain classifier for Mars rovers, which can tell the terrain types on images based on textural features. And unmanned aerial vehicles, both Perseverance and Ingenuity, use AI throughout their mission to land, enable the engineers to remotely aim and control the rover's chemistry camera at the supercam and navigate autonomously. But autonomously, it's used loosely because you could have semi-autonomous and then human in the loop and human out of the loop. The Mars Express, which is in orbit around Mars since December 2003, also has an instrument called the Mars Advanced Radar for subsurface and ionosphere sounding, or MARSIS. So this tool has been designed and built to look for liquid water on Mars. So as you can see, the geomatics is not just on the surface, but also from in orbit as well. Next slide, Vishal. Space weather. So this is another area in which we can use machine learning and AI to help to develop models that can predict what the weather will be like, which is the same thing that we do in meteorology on Earth. But the Martian probes that are in orbit and the rovers can collect weather data, and then that data can be leveraged with deep learning and machine learning to understand weather patterns and then make predictions based on that, so that you can do better scheduling of human work and predict when it's safe, not just to land, but for when humans can work out of the vehicle once they're on the surface. Now there's already an Apple software called the Trinity AI, which is a no-code kind of platform. And as you know, no-code is the latest fad when it comes for development of systems, architecture. And what it does, it allows non-developers to produce deep learning geospatial models. So it's making the technology more accessible to people other than hardcore coders. They can develop geospatial models, particularly on mobile phones operation systems. So as the technology
Tabitha, you have
evolves,
2 minutes left, just letting you
okay,
know. Thank you.
okay. So move on to the next slide, Vishal. Vishal. Okay, so just as you could predict when is the best time to land, you could also use machine learning to launch predict when is the best launch window, and it makes your go no go decisions much better. And in order to do this, we have to trust in the technology and trust in the security of these tools. Can you move on? Okay, so one of the things that that has evolved lately is the notion of digital twins. So it's digital twins basically in the industrial sector leverages all the technologies, cloud, IoT, AI, blockchain, virtual reality, and uses all the data that you collect and basically create a twin of the system so that you don't go into a critical mission without having first simulated that mission using your digital surrogate. And it's also evolving into bio-digital twins, which is kind of out of scope for that, for this presentation, but digital twins, both in the industrial sector and in the medical AI field, can be used to first simulate what an ecosystem for Mars on Earth, so that you can be better prepared for settlement when you get to Mars. Can you move on to the next slide, Rochelle? So we've discussed autonomous robots before, but basically I just wanted to draw your attention to the right side of the slide there, where HPE and Microsoft are collaborating to develop space-borne computer 2 and leveraging the Microsoft Azure cloud to use edge computing for ISS products in underground stations. This will enable scientists anywhere across the world who are performing experiments on the space-based computer to use the cloud and seamlessly transmit information and results between it and the Earth. And this is the kind of infrastructure and the technology that we actually need to develop in order to be able to leverage all the other space technology that we have to improve not just geomatics, but all other aspects of the space economy, so that we could improve our technology to get to Mars and then to settle on Mars and not just survive, but to thrive on Mars. And so Microsoft is also using their space to model dust storms on Earth, and eventually this can be used for predictions on Mars as well. Next slide, please. And I'm ending off here. So basically the slide kind of gives you an overview of what we have now, the current state, and what we'll probably have by the year 2040, fully autonomous agents. Google Maps for Mars is the goal. AI companions and support robots with all the underlying technologies that will prepare us for Mars and help us on Mars, because you cannot construct in a radiation system. You will need tunneling to get underground to protect yourself from the radiation while you build a human settlement. And eventually all of that will require the space infrastructure, the connectivity, because there's no Wi-Fi in space. You need the connectivity, the nuclear energy or whatever you'll be having to power your technology for Mars, your AI, your VR and everything. that will enable all of the other technology that we have discussed and that other people probably have also discussed. And I think that is it for me.
Wonderful. Well, thank you very much for your team to presenting. And if you could just very briefly let us know what is the best way to contact you. Oh, now we see all of your names, and I guess people will be able to Google and find you on LinkedIn to follow up with any questions. But with that, we again thank you very much for presenting, and we need to move on to the next session. So I'll see you all there. Thank you.
Thank you.
Thank you.
Bye-bye.
See you.
Thank you.